and gases. Okay? And they can change. So here is the obvious one. If I get a piece of normal ice out of the freezer, stick it in the sun, what happens to it? It melts, well done. It changes state from a solid to a liquid. As we heat up that liquid, it does something else which we're going to talk about later in the demo. Now in here, I have something called dry ice. And dry ice is solid carbon dioxide. We breathe in air, and we breathe out carbon dioxide. And it's minus 78.5 degrees Celsius. It's even too cold for penguins. Okay? And it's in here. And what I'm going to do for you is I'm going to put some into this tank. But don't worry, the fish have all been rehoused. They're a lot happier. They're in a bigger tank. So everybody's happy. I'm going to put some scoops in. Now this is dry ice because it doesn't melt. It doesn't change into a liquid. It does something called sublime. Let's just say the word sublime. Sublime, what a lovely word. And sublime means it turns from a solid straight to a gas. Okay? Right. That should be enough. So, this is subliming from dry ice into carbon dioxide. So, keep that in your head. Keep that in your mind, okay? Now, for my first experiment, what I'm going to do is I am going to light a candle. I'm going to put it into that box. The prediction for you is what is going to happen to the flame.
Okay.
Okay? Yeah? Not yet. Right, that's my job, to give the reason. I know you know as well. Okay, here we are. Alright, there's the candle, it's lit, okay? And I'm going to put it in the box. Now the prediction is it's going to go out. Sure enough, it's gone out, okay? Let's see if I can light it. Can you see? The moment that flame goes into the box, it goes out. Should we talk about fire? Let's talk about fire. Some of you may have seen our show Flashbang Wonderlab, and we talk about the fire triangle. And we need 3 things for fire. 1, heat. Wood is our fuel, well done. Wood is our fuel, and oxygen, well done. Fuel, heat, oxygen are the 3 things we need for fire. The fuel is what we're burning, that's kind of the food is the fire. The oxygen is like us, it needs oxygen to keep it going. And the heat is what starts it. It's like the kick in the backside my wife gives me when I'm being lazy in the morning and not getting things done. Well, that's what the heat is. Okay? Now remember what I said was going on this box. What are we missing in that box?
Sugar.
Go on. Oxygen. We are missing oxygen. Carbon dioxide, which as you remember is subliming from the dry ice, is heavier than air. It's given a scientific term more dense than air. So that carbon dioxide has gone right down to the bottom and pushed out all of that air. So, the question I have for you, if a gas is heavier than air, can I pour it like a liquid? Can I scoop up some carbon dioxide and stop it over a candle and put it out? No. No? Okay, let's have a vote. Who's for yes? Who's for no? Don't be so ridiculous. On what planet do you think you are on? I'm going to sit on the fence and just, because that's the safest thing to do. Yeah, brilliant. Alright, so let's light the candle. Now, I'm very conscious that I look really, really ridiculously stupid doing this, so please don't laugh or I'll have a tantrum. There we are. Cool, then. Yeah, what did you see at the science room? I saw some guy scooping up something invisible. He looks so ridiculous, you wouldn't believe it. But watch. Hold it in there for a bit. There we are. Did you see that? Do you want to see it again? Go do it in slow motion. Don't laugh. So as it's heavier than air, I can hold this container upright, like that, and hold it in there like that. Alright, what does that matter to you? What does that matter to you? Yes, hey, yes, wow. You can pour the gas, you know, an invisible gas over the candle, put it out. Remember I said I'm very clumsy. One thing I'm ever doing is burning myself. And I know that if I burn myself, I run the burn underwater. The water takes away the heat, one of the things on our triangle, and cools the burn down and makes it get better. But we all know we must never ever touch anything electrical with wet hands. So if I've got an electrical fire, the last thing I want to do is pour water over it. So we use carbon dioxide. It takes away the oxygen, puts out the fire, where it is totally dry. Okay? Brilliant. Yeah. The bubbles in the box. Can you see they're floating? Ignore it. Those bubbles are sitting on an invisible bed of carbon dioxide. They can't.
Look at them.
Right. What am I going to do next? Well, no fun, she'll demo. Let's put some boiling hot water into here. You've probably seen films like Harry Potter. Now this is boiling hot water. It's so important that you do not put your fingers in the bowl. Okay? Here we go. Okay, so please do not put your fingers in the bowl, you put it in the mist. And go like that, and go like that. I can see it's cold. Alright? Now this, what the mist is, remember carbon dioxide is invisible. What you are looking at is little droplets of condensed water, a bit like when you breathe out on a cold day. Remember this is boiling hot water. I'm emphasising this for two reasons, for your safety and for the next part of the demo.
Brilliant!
A gas will always take up the area it's in. You can take as much air as your lungs will allow. As you could. That's about it. But my lungs are absolutely full of gas. This entire room is full of gas. That will fill up with carbon dioxide for as long as there's enough dry ice supplying, as long as that bubble to be able to keep its elasticity. Okay? And I want you to imagine we're on the London Underground. Okay? I'm a real underground nerd. And we get on at Stop Line, the Northern Line. And when we get on, the train is absolutely packed. We can hardly move, we're a bit like this. We're like the molecules of a solid. But as the train starts going down the line, we can sort of move around a bit because people have got off and a bit like the molecules of a liquid. But then eventually it's just us, our little group, on that carriage. We're hanging from the ceiling, we're running up and down, we're dancing. We've got a lot of movement, we've got a lot of energy. We are like the molecules of a gas. How am I going to demonstrate this? Well, we're going to go colder now. This is minus like 70% of air. Is changing state from a gas into a liquid. And you can see that liquid slurping at the bottom. Isn't that cool? It's minus 196 degrees Celsius. Alright, so what has happened has changed state into a liquid. Remember I said a liquid doesn't have the energy and movement of a gas. But now that liquid is warming up, the molecules are getting more excited, they're moving a bit faster, and now, because they're turning back into gas, they suddenly need all of that moving again. And that's what they're doing. Is that all good? Yeah? Brilliant. If there's anything you didn't understand, please feel free to catch me at the end of the demo. I'm always happy to explain. Now, before you lot turned up, my young friend there witnessed something. I was having a bit of a practice, and she witnessed something. She said, "Wow, how do you do that?" And I'm going to find out. And I'm going to teach you all about these things. I'm going to use this one. This is called a superconductor.
What's that?
It's something quite incredible. It's made in the laboratory. Okay, it's made in the laboratory, and if I put it on those magnets, these are magnets, does nothing, does it? Absolutely nothing. It's not attracting, it's not repelling. So what I'm going to do is I'm going to put it inside some liquid nitrogen. Okay, so if I'm all hands off the table again.
No hands on table.
They can actually in 3 seconds.
So my superconductor is made out of yttrium, barium, copper, and oxygen. Now a conductor, we know, is something which allows something to pass through it. So you've got heat conductors, but this is all about electricity. And normal conductors like copper, aluminium, you and me, because we've got water inside us, have something called resistance. So imagine I'm trying to get to the exit and some of you are pushing me back. You are resistant, you are offering me resistance. And I'm getting very, very tired, I'm getting hot, I'm losing energy. So if you imagine wires carrying 750,000 volts across the country, they lose a lot of that energy through resistance. Now superconductors, when we get them really, really cold, they lose resistance. What does that matter to you? Well, if like me, or you know somebody who's had an MRI scan, magnetic resonance imaging, they use superconductor magnets which are cooled down by liquid helium. That is very expensive, and that's why MRI scans cost the NHS a lot of money. Cost us nothing, but the NHS a lot of money. Okay? Now I've got a whole load of future scientists right in front of me. This is going to take a long time. If you can find the elements to make a superconductor work at any temperature, preferably room temperature, you're going to be up there with scientists like Ada Lovelace, Michael Faraday, Cecilia Payne, Professor Stephen Hawking. You're going to be rich, you have a blue plaque on your house, because you're going to change the world. MRI scans, which don't need liquid helium, be cheaper. You can charge your phone once a month, maybe even that every other month. Think about how we may travel. Now what's happened is, some of you may have learned about electrons over the Tesla coil. Well, now those electrons in my superconductor have lost their resistance. They're moving a lot more freely, a lot more efficiently. And they create a current, a small electric current, which will induce a magnetic field. And eddy currents will repel the magnets here. Okay? Now it's very important that if I drop this superconductor on the table, you do not touch it and definitely do not lick it. It's minus 196 degrees Celsius. Right then, you ready? Here we go.
Let's see.
Very nice.
Side to side.
It's become a magnet. It's become a magnet itself. But can you see the moment? Did you see it so quick? It's warmed up now. So to get it going again, I'm going to get cold again. I'll do that again for you, just in case those didn't get their cameras out fast enough. Cool. See, this is the future. Do you see how it's moving up and down? So if you think maglev trains, hover cars, the reason why it's hovering and moving is you're actually seeing something called quantum locking. And quantum locking is when it's attracting and repelling at the same time. There's no trickery. I don't do trickery, I don't do magic, I do science.
That
And once
is
again,
magical.
it's got that going. Did everybody see that?
Yeah.
Yeah?
Is it magnetic?
Is that cool or is that cool?
That awesome.
Did that make you?
That's mega
think,
cool.
Did that make you think I really want to be a scientist?
Yes.
Then I've done my job. Thank you very much. My name's Simon. Enjoy the rest of your day. Thank you.